All right. Who is excited for today's chemistry lecture? I'm excited. We're going to finish chapter 5 and talk about a couple interesting people. Icons of stereochemistry. Who is this guy right here on the left? Let's discover. His name is Emil Fischer. That's what I always heard him called. And he lived to be 66 years old. Hopefully I live to be a little bit longer. And when I saw this picture, I thought, those glasses must make your face tired because there's no bows on them, and I guess they'd fall off your face. That's why he's got them tied on. So he won a Nobel Prize in chemistry. He discovered the Fischer esterification, which you all will do next semester and be able to come up with a reaction mechanism for it. And he developed the Fischer projection, a symbolic way of drawing asymmetric carbon atoms that we're going to look at. He also hypothesized the lock and key mechanism of enzyme action. That is the central dogma of biochemistry, structure and function, this lock and key thing. What is a Fischer projection? Well, it's something we write in the 2D, a flat piece of paper, to represent a 3D molecule. A chiral carbon is at the intersection of a horizontal and vertical line, and horizontal lines are coming out at you, and vertical lines are going away from you. So here's the proper Fischer projection. Lines here are going away from you, as depicted here. Horizontal lines are pointing at you. So it's as if you're viewing from right here, and the vertical lines are going away, and the horizontal lines are coming at you. So Emil Fischer worked on a lot of carbohydrate chemistry. So I went and found 10 carbohydrates here. A bunch of different forms of sugar is what I'd call them. And of course in biochemistry I had to memorize all these and reproduce the Fischer projection. So each one of these has 1, 2, 3, 4 stereogenic carbons. And this is a quick and easy way to designate what that is. So all the vertical lines are going away. So this, if you made a model, you'd have to kind of put it in a ring and roll it around to get this view of it. Here's our stereogenic carbon. Here's lactic acid. I always used to think that lactic acid is why your muscles hurt after you work out. And then lately somebody told me that wasn't true. But anyway, right here is the Fischer projection of lactic acid. Here would be our highest priority group, our second priority, our third. I'm circling around like I'm turning the car to the right, but my lowest priority group is pointing at me, so it's opposite. So it is S. One thing we might do with a Fischer projection is rotate it. On the chain, the most oxidized carbon is typically up top. So I want to teach some OChem here. An aldehyde is more oxidized than an alcohol. You can convert an alcohol to an aldehyde with an oxidizing agent. And we can rotate the Fischer projection 180 degrees if we want to for some reason, but we cannot rotate it in a 90-degree fashion. Here's our lactic acid. We can spin this around like this, and everything is preserved, and it doesn't change anything. Now if I try and rotate this 90 degrees and then stick with our convention that these are coming out, these are going away, you can see here that that's not what the model kit would do. So you can't rotate a Fischer projection 90 degrees. You scramble the stereochemistry, you'd have to break bonds and form new bonds to do it. So don't do it. Now with a Fischer projection, it's easy to draw a mirror image. That's one reason why we might do that. So here is a structure of butane. This would be 2,3-dichlorobutane. And we might ask, how many stereoisomers dichlorobutane are there? Before we go there, I'd say this is the highest priority, second, third. Looks like I'm spinning the steering wheel to the right, but hydrogen's coming out, so it's opposite, it's S. Come down here, this is going to be 1, 2, and 3. Once again, it's opposite of what it looks like. But if you do the hand method, I'm going to do the hand method. I put my thumb coming out because hydrogen's going out, first priority, second priority, third, and I got to come around like that, and it looks like I'm turning the steering wheel to the left, which would be S, and since this is coming out, it's R, but I got my right hand. So the right hand knows it. Bromine, that carbon, the methyl group, come over here. Notice these are mirror images. Hydrogen's coming out. I put my thumb out. I'm going to go bromine, carbon, and methyl. So this one's S, this one's R. Look at this slide in practice with your hands. What are distereomers? They're stereoisomers that are not mirror images of each other. So they're not enantiomers. Enantiomers are mirror images that are somehow distinctly different, meaning non-superimposable. And we've looked at this molecule quite a bit already. I had the models, I wrote them on the board. We had make-believe bromines. Here's methyl groups. Notice these are mirror images. The hydrogens are reflecting methyls, hydrogen on the outside and down, hydrogen on the outside and down. So these are enantiomers. This thing here, distereomers here, and also a distereomer there. So now on to the Fischer projection. I have two stereocenters. And now we can have two that are not mirror images, and so we call these distereomers. When a compound has two or more chiral centers, they have enantiomers, distereomers, or mesoisomers. We've looked at a mesoisomer, but I haven't called it a mesoisomer because we weren't to this point yet. We'll see what a mesoisomer is. Enantiomers have opposite configurations at each corresponding chiral carbon. Distereomers have some matching and some opposite configurations. And what makes a meso compound it has an internal mirror plane. So here's a little bit of math. In OChem, the maximum number of isomers is 2 to the n, where n is the number of chiral carbons. So if I have two chiral carbons, 2 to the second power is 4. I should have 4 stereoisomers. I may have less if I have a meso compound. So imagine a carbon chain and there's 2 chiral carbons, and we have this configuration 2R, 3R. Its reflection is going to be 2S, 3S. So these are enantiomers. If I encounter something that's 2R, 3S, that's a distereomer relationship there. So here I have 2R, 3S, here's 2S, 3R. So these two are reflections, they're enantiomers. So these two things connected by the red line are also distereomers. So is everybody clear on our stereoisomers? Some are convinced, some are not convinced. This ought to put it all together. We have constitutional isomers, meaning they have the same chemical formula. So these are all C5H10, but they're all connected in different ways. All right, then we have stereoisomers, meaning they all have the same order of connection, but somehow in 3D space they're different. So here we have enantiomers. These are all mirror images and they're non-superimposable. So what are distereomers? Well, these aren't mirror images. They're not superimposable. There are cis-trans isomers, and so the order of connection is the same, but how they point out in 3D space, these two are opposite sides of the ring. These bromines are on the same side of the ring. So these are enantiomeric to each other. So these are both 2,3-dibromobutane. They're not mirror images, so they must be distereomers. So meso compounds. So we looked at this one, and I go back and watch the video. I drew 3 structures on the board. I drew this one, the other enantiomer to this thing. Meso compounds have a mirror plane that goes right through the top. What that means is, if you look at this reflection in the mirror, you can take that one and rotate it and superimpose it. So this thing does not have an enantiomer. It is superimposable with its mirror image because it has this line of symmetry here. Same thing here with the cis 1,2-dibromohexane. And so each one of these is a meso compound. Here's the Fischer projection. because we see a line of symmetry right through the middle. So meso compounds are achiral even though they have chiral centers. So the 2N rule, so let's just think about 2,3-dibromobutane, 2 chiral centers. So I go 2 raised to the 2, I get 4. Well, that's the maximum. We could have 3. And here is an example where we have 3. Here's one configuration. This is the assignment. Here's the mirror image. You can notice it's opposite. So these are non-superimposable mirror images. They're a pair of enantiomers. And then we come over here. Since this thing is symmetric, here's this rotation of a Fischer projection by 180 degrees. If I just flip this end for end, I get this thing over here. So it's the same compound. And I try not to spend any time not sleeping at night due to this configuration thing. Sometimes I do, sometimes I don't. What you want to look for is the mirror plane. Properties of distereomers. Yesterday we looked at properties of enantiomers. That was interesting. Distereomers have different physical properties, unlike the enantiomers. So we can easily separate them by density, distillation, melting point, all those things. We separate chemical compounds by their differing physical properties. Enantiomers differ only in reaction with other chiral molecules and how they rotate plane polarized light. Enantiomers are difficult to separate. So this is both butene. I'm an old school IUPAC guy. I just call this 2-butene. We got trans and cis. And we can see this has no dipole because these vectors cancel each other out. This here has an overall dipole moment. So notice the thing that has a larger dipole has a larger boiling point. So this has larger intermolecular forces. So these, in theory, could be separated by perhaps distillation. And so here's a pair of enantiomers. They have a melting point of 158. This enantiomer has a melting point of 256. So you could cool these things down and get this to crystallize out. You could separate. Distereomers are easy to separate. You could separate this from either of these due to the difference in melting point. Both these have the same melting point. They would be difficult to separate. Who is this guy? When you go to the store and you buy pasteurized milk, what does that mean? And why do we call it pasteurized milk? It's to honor this guy. He came up with this thing called pasteurization. He came up with this thing called germ theory. He did experiments and he disproved spontaneous generation, where people thought flies spontaneously generated out of a chunk of meat. Maggots just magically appeared spontaneously. All right, well, you take a piece of meat, heat it up and cook it and seal it off. No flies will ever get in there. Flies come from somewhere. All right, interesting story about Louis Pasteur. He actually, what today we'd say he went to university and he was a physicist. And he was studying light and the nature of light and polarized light, all this good stuff. And he noticed that tartaric acid derived from grapes rotates plane polarized light. You go into the lab and you synthesize tartaric acid, put it in the polarimeter. It does not rotate plane polarized light. And it was a big conundrum. People didn't know what was going on. And he was looking under a microscope at tartaric acid crystals derived not from wine, but from a chemical flask. And he noticed that the crystals were similar, but different. He noticed that this one is a mirror image of this one here. And so he pulled out a pair of tweezers and he separated these crystals. I'm hoping they were big, fat, rock salt-like crystals. And once he got all these crystals separated, he put this one into the polarimeter and it would rotate light one direction. He put this solution of this crystal in the polarimeter and it rotated light the other direction. And he solved the big problem of stereochemistry. They didn't even know it was stereochemistry. They didn't know what was going on, but he figured it out. So the man-made tartaric acid was a racemic mixture. So the plus and the minus mean it has both these enantiomers in it. And then he probably figured out which one's the natural form and which one is the man-made form. What other great things did Louis Pasteur do? So he came up with germ theory. He came up with pasteurization. He was one of the first persons to develop vaccination. He came up with an anthrax vaccination. Have you heard of anthrax? It used to be a horrible thing that wiped cattle out. And so he's over in Europe and he comes up with all this stuff. And the veterinarians over there, how were they? What do they say in Britain? They weren't very accepting of it. And they said, what's this physicist trying to tell us how to take care of our animals? And so nobody wanted to use his vaccination. They were skeptical of it. They were what I would call superstitious. And he fought them for a long time. And finally, there's like anthrax outbreaks, horrible. And he finally said, look, we're going to do this test. We'll vaccinate this group of animals. We won't vaccinate this group of animals. And so finally they came around. So that's quite an illustrious career. Solved the stereochemistry problem, come up with germ theory, come up with pasteurization, develop vaccination.
Did he get a Nobel Prize? The other guy got a Nobel Prize. Did he get one?
I don't know. Wikipedia didn't tell me that when I was doing my research. All right, that's it for today.